Welcome to our Sit Online. I'm Rita Samuel from the Department of Electrical Electronics. The lecture is on the topic state machines. So what are state machines? So we have seen previously in our synchronous counter design and sequential circuits that the output depends on the present state and also on the input that is provided. So usually we can also call a synchronous sequential circuit as a finite state machine. The effect of all previous inputs on the output is represented by a state of the circuit. The output of the state at any time depends upon its current state and the input. The relationship between the inputs, the output, the present state, and the next state can be explained using a state table or a state diagram. So what is a state table? So state table in general is a table that represents the relationship between the present state, the next state, and the output. And we can graphically represent the same information using a state diagram. So first I'll explain what a state diagram is with a very simple example. Here it does not specify any case. This is randomly taken. So what we like to understand. So if we get such a state diagram, what do we understand? We can see that the circles denote the states. So we have 4 states in our system. And the 4 states, we know that the arrows indicate from one state to the other state direction. So when we provide an input of 0, the state from an initial state of 0, 0 goes to the next state, which is 0, 0 itself, and the output is 0. While when we are at the state 0, 0 and we provide an input of 1, from the arrow we can see that we go to 0, 1 and our output is 0. So the direction from one state to the next state is indicated by these arrows, and over the arrow we note input / output, where it shows when an input is given, where it goes and what the output is. Similarly, when we are at 0, 1, when we provide an input of 1, we go to the same state 0, 1 and our output is 0. And when we give 0 as an input, we go to the state 1, 1 and output is 0. So this is how we interpret from a state diagram. The same information we can represent in a state table. So in state table, we have the present state, the next state when our input is 0 and when our input is 1, and corresponding output when input is 0 and input is 1 when we are at the present state of 0, 0. So when we are at 0, 0, when we give an input of 0, we know we go to 0, 0 and our output is 0. While when we give an input of 1, we reach the state 0, 1 and our output is 0. So this can be written in the table as such. Similarly, for all the other states, we can complete our state table as such. So in general, there are 2 types of state machines, that is the Morse circuit and the Mealy circuit. So in Morse circuit, we can see that the output only depends on the present state. That is, you provide an input to your state logic and you have a memory to hold on to your states. And when you give a clock, we obtain an output. And this output is just depending on the states that we receive. While in a Mealy circuit, what we can see is that when we provide an input, the input is also having an effect on our output directly. So for Mealy circuit, the output is a function of input and the current state, while in Moore it depends only on the current state. So we can go to the steps of designing a state machine. In general, these are the steps. That is, first you have develop a state diagram for the function that is required. Choose the required flip-flop and we must be aware of its excitation table. Then we must develop the state table with the present and the next state. We have to create a state equation for the flip-flop using a K-mat, and using this logic we can obtain the circuit diagram. So these are the steps in general. We can see this in detail in the coming slides. Consider the example that you have a design a sequence of 101 and we are considering the melee machine state. So what was melee? Melee depends, the output depends on the input and the current state. So designing a 101 sequence detector means, suppose I have an input sequence as such, that is 001010. This is just an example taken. So suppose if we have an input sequence of such, we can see that whenever in the sequence you have 101, the output, it should output 1. So initially our sequence started with 0, so the output is 0, 0, next came 0, 0, 1, 0, 0. And when we get a sequence 101, it should output 1. Similarly, this continues and when it gets a sequence 101, it outputs 1. Now for this case, we can think of two different approaches. That is, we call it as an overlapping case and a non-overlapping case. So this is a non-overlapping case, what we have just seen. It could also have an overlapping case. That is, you can see that here there is a 101. Then again, if you start the sequence from here, you will have 101 and an output 1. So this is an overlapping case, while here it is a non-overlapping case. That is, we don't want it to be overlapping. We don't consider this one as the starting. We start the sequence from this 0. So we can design according to our interest for either non-overlapping or overlapping depending upon the user definition. So we can now decide for a non-overlapping case. So non-overlapping case is this one. So the state diagram, we will see how we can draw the state diagram for this case. So first we have the state. So this state means we are at the start state. We don't have anything. We are ready to accept the sequence. So at the start state, when I get a 0, I know my sequence haven't started. My sequence starts only when I get 1. So when I get a 0, it means I'm still at the starting point. But when I get 1, I can move on to the next state. That is the condition where I get the first digit of my sequence. But in both the cases, I have not obtained the required sequence of 101. So my outputs will be 0 in both the cases. So once I obtained 1, I go to the state S1 where I have 1 in my hand. When I am having 1, if I get a 1 again, my output is 0 and I will still be in again the state 1 because if I have to move to the next state of my sequence, I need 1, 0. So I need 1 and 0. If it is 1 and 1, I reach the same state again. I'm still with 1 in my hand. So if I get a 0 when I'm at state, now I am in the condition that I have 1 and 0 with me. So when I get 1 and 0, I reach the next state, and in this state of 1 and 0, I should get a 1 to complete my sequence. When I get a 1, I can output 1 because now I have my inputs as 1, 0, 1. So my sequence is detected and an output 1. And then again I go to the starting state because it's a non-overlapping case. While after getting 1 and 0, again I get a 0, it means my sequence is not detected. So I go to 0. So now I have a 0 in my hand, which means that I go to the starting point again. So this is how we draw the state diagram depending on what is required. So the state definitions are, when we are at the state S0, I am in the reset state. That is, I have a sequence of 0, 0. When I am at the state S1, it means I have got a 1 with me. When I am in state S2, it is a state where I have 1, 0 with me. And at state S0, S2, when I get a 1, my sequence is completed and thus I can output 1 saying that I have detected the sequence 1, 0, 1. So now we have obtained our state diagram. We have to draw a state table. In the state table, we know we have the present state. We have 2 bits over here for the state S0, that is 0, 0. State S1 is 0, 1, and state S2 we can represent as 1, 0. So we have 3 states represented as 0, 0, 0, 1, 1, 0. And the inputs we have 0, 0, 0. Also we can have 1, 1, 1 when we are in these 3 states. Over here I have included the state 1, 1. We know that we don't have a state 1, 1, but still since we are using 2 bits, our 2 bits can also have the values of 1, 1. But it is considered as a don't care case because we are not included that in our state diagram. Now this is the present state. So when I am at 0, 0 and when I obtain 0, my next state is 0, 0 and my output is 0. That is according to the state diagram. Now I have chosen a D flip-flop for my design. We know according to the excitation of D flip-flop, whatever output you want to receive, you have to put that as the input. So I am looking at Q1 and Q1 star to design my D1. So Q1 star is 0, which means I want 0. So the input to D1 should be 0. And next one, Q1 is 0 and next Q1 star is 1. So I want the output as 1, which means my input to D1 should be 1. Similarly, we can fill the values for D1 and D2. So once we have obtained our state table, we can go to obtain our state equation. So that is, we have to obtain a relationship between D1 and the input and present state. We have to obtain a relation for D2 with the input and the present state. Similarly, we have to obtain a relationship for our output with respect to the variables input and present state. So we have 3 variables, that is the input, present state, Q1 and Q2. So based on the state transition table, we can write our K-map for D1, D2 and our output, which is represented by the term Y. So after filling the K-map, we know how to simplify using K-map using the SOP technique. We obtain the expression for D1 as X bar Q2. And here we obtain the expression for D2 as X Q1 bar and the output Y as Q1 X. So using these equations, we can now design our logic circuit. That is, we have 2 flip-flops. This is D2 flip-flop and this is D1 flip-flop. And we know from the expression that D2 is X Q1 bar. So it is X Q1 bar. And D1 is X bar Q2. And our output is Q1 X. So we can see this is a Mealy design where our input has direct effect on our output. So the output depends on the current state and also on our input X. Now we had considered the non-overlapping case. We will see the state diagram for overlapping case. Similar to the previous one, when we are at H0, we can have input 0 and inputs 1. When we have the input 1, means that we got the first value of our sequence. So we go to the state S1, and when we have 0, we remain in the same position. And similarly, when we are at S1, it means that we have got one of our sequence. If it is 1 again, it means we remain there itself. While if we get 0, we go to the next state where we have 1, 0. So since it is a design for an overlapping case, now we have 1, 0. If we get a 1, we can again go to the state S1 saying that I have got 1 in my hand. So which means that again it is 1, 0, 1 and you can detect the sequence as 1. While when you are having 1, 0 and again you get 0, it goes back to the starting table. So this is the difference when we have for a overlapping case. So with respect to the state diagram, we can obtain the state table. So the difference comparing to the previous case is that over here, when we are at state 1, 0 and we give a 1, we go to the state which says that we have a 1 in our hand. So vice versa, that it changes for our output and the values for D1 and D2. The change in state table for overlapping case and then continue. This is the only change we have comparing to the overlapping case, and then we continue as explained before for the state equation and the logic circuit. Now you will see how we design the same sequence detector using a Moore machine. So in Moore machine, the major difference is that we have to have a state diagram, and in this state diagram we have the state and the output is written with the state itself. So the output is with respect to the state. As mentioned in the previous case, we had the input / output depending on the input provided. Here the output is with the state. So when I am at the state 0, I can receive a 0, which means I'm still at the same state. I can receive a 1. So I reach the next state where in state S1, it is a state where I have a 1 with me. But still the output is 0 because the sequence is not completed. At that state, I can receive a 1, which still is the case where it says that I have a 1 with me. But in state S1, when I get a 0, it means I go to the next state where I have 1, 0. And the output is still 0 because the sequence is not completed. At this state, when I get 1, I go to my third state where I have 1, 0, 1. And I output that I have detected my sequence and I have a 1. While in state S2, we know we have 1 and 0 with us. The last two bits are 1 and 0. When I get again in 0, it means I go to the state where I have a 0 with me. Now, in state S3, when I am in S3, I have 1, 0, 1. When I get a 0, my last two bits, that is, it is 1, 0, 1, and I get a 0 again, which means that I reach the state S2 again, where I have 1, 0 with me. While in 1, 0, 1, if I give an input of 1, I go to the state S1, but still my sequence is not completed, so it is 0 again. So in this Moore, we can see that we have more states because we have for each state there is an output. And state S0 means I am having 0, 0 with me. The state S1 means I have the last bit of my sequence is 1, which is agreeable for the detecting sequence. When I am S2, it means that I have 1, 0 with me. When I am at S3, I have 1, 0 with me, 1, 0, 1 with me, which means it's the required sequence and I have to output 1. So when I am at 1, 0, 1, when I give a 0, now at this stage what I have is 1, 0, 1, 0. So the last two bits are 1, 0, which is a part of my sequence. So that is why I go to the state S2. So the design over here we have considered is for the non-overlapping, is considered for the overlapping case. If it is for the overlapping case, we'll have to change accordingly. So with the state diagram, we can now compare with the Mealy state diagram. So this was the Mealy state diagram where we have seen we have only 3 states. While in the Moore we have 4 states. So here we can see for the state S2 and consider for the melee, when we input 1 and when we input 0, we have different values of our output. We have two different values of output. But that is not possible in Moore. For a single state, it just have one value for its output. So in melee, we can see when we provide 1 as input and 0 as input, our output is 1 and 0. While in Moore, for every state, it should have only one output. So that is why we take another additional state for Moore. So with respect to this state diagram, we can similarly write the state transition table as mentioned before. We have two bits Q1 and Q2 and vice versa we can write the state table. Now from this table we can write the K map and we can obtain the expressions for our D flip-flops. So here we can see that our output Y is depending only on Q1, Q2. The term X is not there, input is not there. So for a Moore design, the input is not affecting the output. So based on this relationship, we can draw the circuit diagram. And here we can see that the X does not have a direct connection to the output. It just depends on the current states Q1 and Q2. So this is in brief the difference between melee and Moore. We can see that for Moore, the output depends only upon the present state, while for melee, the output depends on the present as well as the present input. The input changes, output does not change for a Moore. The output depends on the state, while for melee, input and the present state will affect our output. In Moore, we have seen that we require more number of states, while in melee, we require lesser number of states. Therefore, since we have more states, it means that we require more hardware, and melee, we require lesser hardware. Moore reacts slower, definitely, as it has more hardware, and melee reacts faster. In Moore, it is synchronous to the output and state, because once the state is there, it is synchronous with respect. While in melee, it is asynchronous because it depends on the change of the input also. While here it is on the states, and the states change with respect to the clock. The output is placed on the state and the output is placed on the transition. Moore is easier to design, while melee is more difficult as it depends on the input also. Thank you for your patient listening.